I can pretty easily say that the one tool that's had the biggest impact on my productivity as a web developer is TypeScript. And that's pretty amazing considering a few years ago I had no interest in learning it and was only exposed to it because I had a client that required an Angular app. In today's video, I'm going to show you all the basic concepts needed to be successful with TypeScript, and I'll throw in a few pro tips here and there that I find especially useful. If you're new here, like and subscribe, and there will be a t-shirt giveaway with this video. All you have to do is leave a comment below and we'll pick a random winner next week. I want to start with a shout out to Basrat Syed, who is the author of the TypeScript Deep Dive book. It's my go-to resource for advanced concepts, and it's free and open source. So originally I was resistant to even learn TypeScript because I wasn't super comfortable with strong type languages, and I really try to avoid writing any more code than I have to. But this is a situation where writing a little more code up front will pay big dividends as your project grows. The biggest benefit is actually just tooling, which you get in your IDE like VS Code. When you use type annotations or work with libraries that are strong typed, your code will be automatically documented in the IDE, so you rarely have to refer back to online documentation for the libraries that you use. In addition, the compiler can catch bugs in advance, which is a far more efficient way to refactor code. I think this Reddit post says it best: would you rather have silly errors during development or insanity-inducing errors in production? Another cool benefit of TypeScript is that there's virtually no learning curve if you know JavaScript. That's because it's a superset of JavaScript, so any valid JS code is also valid in TypeScript, so you can learn it incrementally as you go. And it also allows us to write our code with future JavaScript features without having to worry about whether or not this code will be supported in our environment, because we can transpile it to multiple JavaScript flavors. Now that you know TypeScript is awesome, let's go ahead and get started. The first thing you'll want to do is install TypeScript globally with npm. Doing this will give you access to the tsc command, which will run the TypeScript compiler. At the time of this video, I'm running version 3.1. So the first thing we'll do is create an index.ts file, and TypeScript code on its own can't run anywhere. It won't work in the browser or in Node.js or anything like that. What we do is use the TypeScript compiler to convert that TypeScript code to vanilla JavaScript. Let's start by writing some plain JavaScript in our TypeScript file and then compile it. So we'll just say console log hello world, then we'll go down here to the command line and run tsc index.ts. You'll notice that creates an index.js file. That's our actual JavaScript code that we can run in the browser or Node. And because we just wrote plain JavaScript, the code is identical to what's in the index.ts file. By default, TypeScript will compile to ES3, which doesn't have support for async await. So let's see what happens when we write an async function in our tsc file and then compile it. So you'll notice here that our code gets transpiled to this crazy looking JavaScript just so we can use async await in our main TypeScript code. The compiler is actually very sophisticated, and there's a ton of different options that you can pass to it to customize its behavior. You could pass these options in from the command line, but the standard way to do it is to create a tsconfig.json, which will automatically get picked up when you run tsc. The tsconfig can seem pretty overwhelming at first, but there's usually only a few options that you have to think about for the most part. The first one is the target, and this is the flavor of JavaScript that your code will be compiled to. So if we set our target to ESNext and then run tsc, you'll see that it compiles our code with async await natively because it's targeting the latest version of JavaScript which supports that syntax. Another option that we'll want to set right away is watch true, which will just recompile our code every time we save the file. That'll just save us from rerunning the tsc command after every change. The next option we'll look at is lib, which allows us to automatically include typings for certain environments such as the DOM or ES 2017. So if you're building a web application, you'd want to include the DOM library, which allows TypeScript to compile your code with all of the native DOM classes without any compilation errors. For example, if we go back to our code, we can use the URL class, which is part of the DOM, and we'll get autocomplete and IntelliSense on this class. So this is where the incredible tooling of TypeScript starts to come in. If we hover over the class, we have integrated documentation, as well as an error message telling us exactly why this code won't run. And if we want a really explicit view of the interface, we can right-click and go to the typings. Then we'll have a view of every property and method that exists on this class. But usually that's not necessary because all this stuff will just autocomplete for you as you start typing. The next thing we'll look at is the use of third-party libraries. So let's go ahead and install Lodash with npm. And you'll see that creates a node modules folder with the source code for Lodash. A lot of mainstream libraries like Firebase, for example, ship with type declarations automatically. But Lodash is not one of them. So if we go into our index.ts and import Lodash, we'll get a warning from TypeScript saying that there are no declarations found, which means we're not going to get any autocomplete or IntelliSense in the IDE. But the good news is there's a giant mono repo out there with community maintained types. If we go ahead and install the types in our development environment, we'll have autocomplete and IntelliSense for every Lodash function. So now that we know how the TypeScript compiler works, let's go ahead and write some code that uses type annotations. There are two ways you can strong type your code, implicitly or explicitly. So let's say we have a variable that should be a number. If we assign a value to this variable when it's declared, its type will automatically be inferred. As you can see here, it's a primitive number type. Then if we go down here and try to assign a string value to this variable, it's going to give us an error because a string is not assignable to a number. If this code were vanilla JavaScript, we wouldn't catch this bug until we actually run our code somewhere. But with TypeScript, we know about it right away. Unlike languages like C# or Java, we can actually opt out of the type system by annotating our variable with any. This just means that this variable can be assigned any value and the compiler won't type check it. Ideally, you want to avoid doing things like this when possible, but it does give TypeScript a ton of flexibility. In the last example, we gave our variable an implicit number type, but what if we don't have a value to assign to it up front? If we don't add any type annotations to it, it's going to be inferred as an any type. So we can assign both a string and a number to it. If we want to annotate it with a type, we can just do colon followed by number, which is one of the built-in primitive types in JavaScript. When we do that, we get an error under the string value because we can't assign it as that type. One tip that I'll give you here is that if you have an implicit type, don't bother explicitly strong typing it. For example, here we're assigning a value that's a number, so adding the number annotation is really just redundant. So we've looked at some of the built-in types in JavaScript, but you can also create your own types from scratch. First, you'll give the type a name, which is typically in Pascal case. And for right now, we'll just go ahead and arbitrarily assign our style type to a string. Then we can declare a variable that's annotated with this style type. And then we'll get feedback for this custom type instead of just a regular string. Right now, this is super redundant, but let's say our style type can only be bold or italic. We can create a union type by separating them with a pipe, and now we can only assign this variable to these two specific values. And we're not limited to just strings, we could even extend this custom type with a number. So that's pretty cool, but more often than not, you'll be strong typing objects that have multiple properties with multiple different types. Let's imagine we have two objects, and we want to enforce that this object shape has a first and last name with string types. Composing objects or class instances that don't have the correct shape is an easy way to create bugs in your program. But with TypeScript, we can enforce the shape of an object with an interface. If we know that the shape of the person object will always be the same, then we can define an interface that defines the types on each property. Now we can use this interface to strong type these objects directly, or we could use it as the return value from a function, or as an argument, or anywhere else in our code. Now, sometimes an interface like this can be a little too restrictive, but you can actually maintain the required properties and then add any additional properties to be added by creating a key with a type of string, with a value type of any. So now a first and last name will be required, but you can also add any additional property that you want to this object. Now let's go ahead and switch gears to functions. Strong typing a function can be a little more complex because you have types for the arguments and also the return value. So here we just have a plain JavaScript function without any types that raises x to the power of y. So currently we could add string values as the arguments here and we wouldn't get any error from the compiler. But obviously this function is going to fail if we try to pass it any non-number value. You can annotate arguments the same way we do with variables by just adding a colon and then the type after it. And that will ensure that only numbers can be passed to this function. So the function implicitly has a number return value because we're using the native math JavaScript library, but we can annotate a specific return value type after the parentheses and before the brackets. So if we set that type to a string, you'll see it's underlined in red because it's returning a number. To implement this function correctly, we can call toString, which will then clear out that underlined error. And in many cases, you might have functions that don't return a value or create some kind of side effect. In that case, you can type your function return value to void. So you'll commonly see the void type on functions like event listeners or side effects that just don't return a value. The next thing we'll look at is how to strong type an array. So we'll start by creating an empty array and then pushing a few different values to it with different types. We can force this array to only have number types by doing a number type followed by brackets signifying that it's an array. Now you can see we get an error every time we try to push a value that's not a number. This is especially useful when you're working with an array of objects and you want to get some IntelliSense as you're iterating over those objects. For example, if we retrieved an array of people from our database, we could use our person interface to know the exact shape of those objects as they're retrieved. TypeScript also opens the door to a new data structure called a tuple. These are found in other programming languages like Python. And basically they're just a fixed length array where each item in that array has its own type. So we can name our type myList, and then we'll give each of its values a different type. Currently this is giving us an error because we're initializing this array as an empty array, but the compiler is expecting all these values to be defined up front. So one thing you can do is make these values optional by putting a question mark after the type. And you can also use this question mark syntax in other places in TypeScript, for example, to make function arguments optional. The last thing I want to show you is TypeScript generics. You may run into situations where you want to use a type internally inside of a class or function. A good example is an RxJS observable, which itself is just a class that has an internal value that you can observe. So the capital T in this code represents a variable type that we can pass in to strong type this observable's internal value. So this allows us to specify the internal type at some later point in our code. For example, we might have an observable of a number, or maybe we have an observable of our person interface. And we can also do this implicitly. If we create a new observable of a number, it's going to implicitly have that internal number type. So more often than not, you'll be using generics rather than creating them, but it's definitely an important thing to know. I'm going to go ahead and wrap things up there. Hopefully this video gave you an idea of why TypeScript is so powerful, but we really only scratched the surface here. I'd like to do a video on object-oriented versus functional programming in TypeScript, or possibly decorators, so let me know what you want to see next in the comments. If this video helped you, please like and subscribe, and if you want to learn more, consider becoming a pro member at angularfirebase.com. You'll get unlimited access to my full-length courses, as well as project support on Slack. And of course, I will mail you this laptop sticker that you see on the screen now. Thanks for watching, and I will talk to you soon.